All right. Moving on now to the third of the last conservation laws, which is the conservation of energy. Now, energy is something that is different than what we've been dealing with momentum, both linear and angular momentum, in that it's both in some ways more complex, but also simple. Simple in that we are going to be dealing mostly with scalars instead of vectors. So rather than having to deal with multidimensional quantities that may or may not be conserved, we can talk about a single number, that is, whether that may or may not be conserved. How it can be more complex, however, is, if you think linear and angular momentum, right, there really was only one way to write down momentum, m times v. And it could take multiple forms based on the sorts of motion that things were doing, but nonetheless, it all came down to just m times v. Where energy can also have multiple different forms, but in very complex and unique ways. These things called kinetic energy, which depends on masses and velocities, and then potential energies, which can depend on spring constants or gravitational constants, or thermal energies, or light has energy. So energy, while a single scalar number, the vast variety of forms it can have does make it a little bit more complex in that regard, in contrast to momentum and angular momentum. In many ways, though, energy and the idea of potential energies arising from forces may be one of the more fundamental aspects of how we describe the real world today, at least in modern physics. The idea of energies and potentials really are what pervade all higher order branches of modern physics. And so energies are defined. So energy, we can start to begin by defining. And how does it relate to forces? As forces being applied over distances. Over distances. This is different than the momentums, where we asked how does momentum change? Then it was forces being applied over time, or torques being applied over time. Now we're talking about forces being applied over a distance. As the box moves across the table, there is motion associated, that there's, the object is moving over some distance as a result. I can talk about this thing called energy in those contexts, though I cannot really talk anything about energy when I say just push my hand up against the wall. Nothing is moving in that case, so there's really no exchange of energy in that case, though you can think of it as an exchange of momentum. I'm pushing on the wall over time, I'm trying to transmit momentum to the wall, but then other forces, like the fact that the wall is attached to, say, the ground, can also act on the wall and can take away that momentum so that the wall ultimately doesn't move. That is different, because then you can think of it as a flow of momentum, where you can't really say that with energy, because nothing is moving in that context. I didn't transmit or do anything in terms of energies when I push against the wall and nothing moves. So this makes the math a little bit more difficult, in that if I have some initial position, r sub 1, and then it takes some path over to r sub 2, that displacement is a path that it took. And that's one possible path. Another path it could take is could round out and loop around and go here. That's another possible path it could take to get from R1 to R2. Or it could go back a ways, up, around, loop a little bit, then eventually make it to R2. That's a third possible path. And I think friction is a nice way to imagine this, how you can see how these paths could result in different answers. If this entire surface is sand, and I'm trying to roll a ball across the sand, each of these paths is going to require a certain amount of effort and a different amount of effort to get it from point A to point B. And if the ball was rolling on its own, you might imagine the sand is going to slow down the ball more in some particular cases versus others. So this is what we're trying to get into, of thinking how forces do stuff over distances. And so we define work. over some distance dr. So in traversing this path, I take a little step going back here. It could be maybe I start here and I move out here. Right? This would be a little dr. And this black path would then be comprised of a bunch of tiny little drs, which in the calculus limit you can imagine can become an infinite number of these little steps, and I can assess how much forces are doing over each of those little distances for every little step. So we can define work over some dr as, and since we're doing it in the calculus limit, we'll say dw, a little bit of work, is equal to that force dotted with the path that you're taking, that step you've taken. This can be the definition of work over some small little step. It is forces, again, being applied over distances. Notice it's not F times dt, it's F dotted with another vector dr. It's a dot product. Dot products return back scalars. This entire thing is going to be a scalar. Work is a scalar, not a vector. And so as you march along some path and you feel a force acting on you, maybe it's sand that's trying to push back on you via friction, or maybe you're trying to walk, from my house to your house and there's a strong wind outside blowing in a particular direction. You can imagine a force vector being associated with that wind, with the wind that's blowing on you. You can imagine in certain cases if the wind is at your back, that might be pushing you along the path, and you might imagine in that case, if there's a force pushing against your back, that since the force and the net force is kind of in the same direction as maybe your velocity vector, that might cause you to speed up. Versus if the wind is at your face and pushing against you, in that case the velocity vector and the force vector are anti-parallel, you might imagine that's going to slow you down. Or if it's at some angle, or you get a strong wind pushing you to the side, you feel yourself kind of veering over. It's trying to change your direction. So what of these can work tell us in terms of if I calculate the net work that I do over, say, a long extended path rather than just a single little calculus step? Well, let's start back from the beginning. So a little bit of work is a force dotted with some little step. Force, of course, by Newton's second law of motion, is just the mass times the acceleration, which I'll write as dv dt, dotted with some little step. And now I'm going to do a little mathematical magic and rearrange this a little bit and write this as dr over dt dotted with dv instead. So again, thinking of the derivative as a fraction. Again, the mathematicians will laugh at us, but this works out. When you do it more rigorously, this is also still okay. This dr by dt, of course, is just velocity. So I can write this as m times the velocity vector dotted with dv as an equivalent way of writing down work. Which kind of looks like, you can imagine if I divided everything by dt, it would say the change in work over time is equal to maybe m dot v or mv dotted with dv by dt. Now this thing on the right hand side is reminiscent of something like a chain rule. So you do enough of these and you start to imagine kind of how this can work. But let me just go off to the side and imagine, what if I was going to do, say, a differential, let me just do it as a time derivative to make it more intuitive, of m over 2 the magnitude of the velocity squared. That might look familiar. We'll see that this will actually be very relevant to what we're doing here. Now, if the mass is constant, then the time derivative comes in, and that's just the same as m over 2, the time derivative of the square of the velocity. But the magnitude, of course, is just the vector dotted with itself. So this is m over 2, the derivative of v dot v. And then by the product rule, that looks like it's then going to be dv dt dotted with v plus v dot dv dt, which, since the dot product commutes, that looks like this is just going to be m v dot dv dot dt. And that ultimately equaled d by dt of m over 2 velocity squared. Now, to help us with this differential, what I'm going to do is notice that the left-hand side has a dt in the denominator and the right-hand side has a dt in the denominator. So I'm just going to multiply both sides by dt. And it looks like in this case the differential of m over 2 velocity squared is equal to mv dot dv. Essentially, we're undoing the power rule and the chain rule in a sense. To take the derivative of the left-hand side, we did the power rule and then the chain rule. We're essentially just going backwards in this case. So then the work, which we again said was mv dot dv, looks like that's the same thing as just the differential of m over 2, the magnitude of the velocity vector squared. And now this has turned into a super easy thing that we can integrate. If we integrate this side and this side, think back to the calculus module, and I'll just do it off to the side, right? The integral of dx, right, we said is just x. The integral of dy is just y. The integral of d star is just star. And whatever is after the d just becomes what's left over once you do the integral. So in this case, if we want to do, say, the net work, that's going from, say, some location R1 to R2. All right, so this might be, starting at R1 and then end at R2. That is a particular path that we're taking. Though, of course, this integral is just an integral of a scalar, so it really only matters what's going on at the endpoints. It looks like in this case, the work is then just 1/2 mv squared evaluated at the end minus the same thing evaluated at the start. Or, since m is just a constant, right, this is just m over 2, v final squared, and I'll get rid of the absolute value signs, minus v initial squared. Whatever the velocity is at the end of the path, minus whatever the velocity is at the beginning of the path, and those velocities are being squared. This, of course, might look familiar. So then if we define kinetic energy, T as 1/2 mv squared, scalar v squared, then we get the work energy theorem, which says that the total work done on an object, or really the net work for a given force, is equal to the change in kinetic energy, or the kinetic energy final minus kinetic energy initial. And this is what's called the work energy theorem. What this is saying is that, just like how for momentum we said forces over time change momentum, torque over time changes angular momentum, work, or forces over distances, change not just any energy, but it changes this quantity that we call kinetic energy. Kinetic energy is changed by work. That is the broadest, most general statement about anything that we can derive with energy. Work changes kinetic energy. And we could take some examples of, right, if you have a force, let's just take an example of I drop a ball and it falls straight down. Well, there's a gravitational force that's pointing straight down. So if I think of the path that the ball is taking, right, all the little steps it's taking, all the steps it's taking are also pointing downward. So F sub g dotted with dr. Well, since those are parallel with one another, right, in this case, are exactly parallel with one another, that's just going to be the magnitude of the gravitational force times the magnitude of the step. And that would be a little bit of work that's done for every time the ball falls a little bit in the air. And that's positive. So I expect that as it falls from, say, my hand to the ground, the net work is then going to be ultimately positive at the end of the day. And unsurprisingly, if we think of what's happening, the ball is accelerating or speeds up, so that t final minus t initial is greater than 0, or that t final is greater than t initial. It is moving faster when it reaches the bottom compared to what it was doing at the top, even if it was moving when I initially let go at the top. If I threw it down, it still speeds up because the force is doing positive work. Positive work speeds up. Or we can kind of just summarize that. If that net's positive, speeds up. If that net is negative, slows down. And again, this is really at the heart of everything that we will do regarding energy. This work energy theorem came up time and time and again, maybe like a half a dozen problems or so on my physics GRE, the kind of exam you take to get into grad school. And it was at that moment, while taking this very hard exam, that I had this insight that really it was the work energy theorem that mattered all along. It's not memorizing MGH and all these other things, which are nonetheless important. But at the heart of it, if I had to boil it down to one thing that was important for energy, it all comes down to this work energy theorem. Work, forces over distances, change kinetic energy. So we can write F net, the net work, right? That's some force that's acting on an object, from R1 to R2 over some path. That equals the change in kinetic energy. Note that the work is a scalar. Note that the kinetic energy is a scalar. So this says nothing. Note this says nothing about direction. Right? This doesn't tell you if the ball is moving up or down. This does tell you if the ball is moving with a certain velocity or speed. Right, so it says nothing about the direction of v, only really the magnitude of v. So in that regard, you might think that we've kind of lost a little bit of information. And it's true that this is telling us different stuff compared to what momentum and angular momentum were telling us, which were more or less just equivalent to Newton's laws. Those were telling you directions and magnitudes. This is telling you something about only magnitudes, but then we'll also find greatly simplifies our lives in terms of how we can solve particular problems. So it's still quite worthwhile. This kinetic energy, if I had to give a phrase of what is kinetic energy. Also, I'm using T because I think that's what our book uses. A lot of the physicists that were related, that studied energy, like Joules and a lot of those physicists were French. So if I had to make a guess, I think the reason why T is common for kinetic energy is because the French word for work is travail. So it starts with a T. That's just a guess. But kinetic energy, what is this saying? If you tell me the kinetic energy of a system, which again, I don't really need to write it down, what is the kinetic energy of a system? You're just adding up the kinetic energy of all the individual parts in the system. T is a measure of how much is going on. In the system. If things are moving around and there's lots of motion associated with the system, that system will have a high kinetic energy. And again, it doesn't say anything about whether that kind of motion is, say, coherent, like a spinning galaxy where everything's kind of spinning in the same direction, versus the air in this room where everything is kind of moving in random directions. It's not saying anything about that, but it's giving you a measure of kind of how much is going on in the system. And this is in contrast to, say, potential energy, which will be the next video, which potential energy is saying something more about how much could happen, in terms of another way of quantifying energy, in terms of things that can come to be, where kinetic energy is saying something about what's happening right now in the system. What about when there are multiple forces? Well, the proof above is exactly identical, where you can say that the network on an object, which will tell you ultimately how its kinetic energy changes, then just is replaced not with F, but with F net dot dr. And that then still equals the change in kinetic energy for that particular particle in the system. And what I want to spend the rest of the time today is reviewing these line integrals. So these are integrals that are over a particular path, which are a little bit more complex than multidimensional integrals, because it's not just a 1D, 2D, 3D integral, but it could be a multidimensional integral, but it's not over kind of a space, but over some sort of particular path that you're taking through potentially 1, 2, 3-dimensional space. There's an image I need, which is why you're seeing that in the corner. All right, which is not what I wanted to do, but for some reason it got big. Let's see here. All right, apologies for that. So let's remind ourselves from Calc 3 how we do these sorts of line integrals. Ultimately, the easiest way I always remember how to do these is that you can just, if you can parameterize the path over some one-dimensional scalar variable, like say t, or you can make up a variable, call it s. If you can describe the path by some variable, you can turn what looks like a complex thing involving a dot product of vectors into essentially a single 1D integral over that particular scalar. So let's do a simple one of just gravity first. Right, so I have some particle here that has some mass m, and based on my origin, it has some position, which might be x, comma y, comma z, even though I'm just drawing this in 2D. And there's a gravitational force that is pointing in the y direction. And if it starts at a height h above the ground, I want to ask kind of from rest, say, starts at rest, how fast is it moving when it hits the ground? And let's have it take the path where it just falls straight down, and then let's have it take the path where it goes down a 30-degree ramp. So the first case, which maybe I'll do it in blue, is the path that just goes straight down. So path 1. So I already know the gravitational force is, in this case, is 0, comma, negative mg, comma 0. And now I need to come up with some sort of path that it's traveling. Now in general, if I look at the r, if I take the differential of this expression, then dr in general is just dx, comma, dy, comma, dz. So every step can move potentially a little bit in the x direction, a little bit in the y direction, a little bit in the z direction. And how much it moves in each direction then constitutes a particular path. In this case, it's not too bad, because if it's just moving straight down, you know that you can simplify this to just being 0, comma, dy, comma, 0. it's only moving in the y direction. So every little step only is changing y. It's not changing x. It's not changing z. So in this case, you can parameterize, if you want to think of this as parameterization, you can parameterize this in terms of just y, in terms of it falling straight down. So then if I want to evaluate the integral of f dotted dr, that then looks like it's the integral of, and I can do that dot product, and it looks like it's negative mg dy, which is pretty simple. It's a constant function, so I don't have to worry about the exact values for x, y, and z, and I now have to constitute what this path looks like. In this case, I'm starting it at y equals h, and I'm ending at y equals 0. So that would be the path that starts at y equals h, falls straight down. There's no dx, there's no dz. And it actually turns out even if there was, it wouldn't matter, since the force, right, the dot product would get rid of the x and the z terms. We'll do a more complicated example later. And then notice that this just ends up being mgh. mgh, which then by the work energy theorem equals the change in kinetic energy, which if I tell you that it started from rest, then that's 1/2 mv final squared minus 0 equals mgh. Or it looks like 2gh all in the square root equals v final. Technically plus or minus v, the square root of 2gh, because again, this does not tell me the actual direction. I have some intuition about what's going on, that I know it's going to be moving downward, so I might actually put a negative sign out front, knowing it's going to be the negative solution that matters in this case. But the work energy theorem wouldn't necessarily tell me that unless I had some other additional insight. Now let's do the path where it moves down a ramp at some angle theta. I think I said 30 degrees, but let's just make it some arbitrary angle. That's between 0 and 90. In this case, path 2, so down a 30-degree ramp, down a theta ramp, there is motion in the x direction and the y direction. So I might want to parameterize the path r in some way that takes me from, I could say potentially takes me from x naught comma h, and then takes me down to wherever this bottom point here, whatever that is, where y goes to 0 and x goes, you can figure that out because it's just a pretty simple triangle. So in this case, it might be nice to parameterize the path. And I think most textbooks kind of always do it in terms of the variable t, right? The math textbooks always do it in terms of some variable t, which you might think if you knew the path as a function of time, that would be a perfectly valid way to parameterize this path. The nice thing to remember about line integrals is that when you're doing a line integral, it does not matter how you parameterize the path. As long as it's a straight line that starts at x naught comma h and goes down to the base along a 30-degree ramp, no matter how you come up with the way it does that, right? It could go super slow and then very fast, or it can kind of zigzag its way down. It does not matter. As long as it draws out the same path, the line integral is independent of the parameterization that you use. So you just have to come up with any way of writing down a parameterization that takes you from x naught h down to the base. So in that case, you might do something like r could be, well, in the x direction, I start at x naught, and then you can work out the triangle relationships. It ends up as a cotangent of that angle multiplied by h minus y, such that when y equals h, this just equals x naught, and as y gets smaller, notice this entire thing gets bigger and bigger and bigger as it goes down the ramp. And then comma, you might have the y direction just be y. It starts at h, goes down at 0, and then there's no z component. This would be a way in terms of the parameter y, right? Not necessarily t, but I'm using the parameter y in this case to parameterize how it starts at the top and ends up at the bottom and follows a straight line that goes down. It's saying nothing about how exactly it gets down, but it does start at the top and ends at the bottom, and that's all you need because it's independent, because the parameterization doesn't matter. I don't think that has a name, or at least I don't remember that theorem having a name. I remember it being just a kind of simple proof. All right, so essentially what I'm doing is I'm going to turn this into a 1D integral over y. So then when I do dr, x naught is a constant, that's 0, cotangent is a constant. Then it looks like I have minus dy, because h is a constant, dy, comma 0. So then this looks like, then it's negative cotangent dy minus, or comma dy, comma 0. And that is my parameterization of the path as y goes from h to 0. All that x stuff actually doesn't end up mattering that much, because then when I calculate the total work, I take this dot product. But again, since gravity only has that the second component is the only thing that's non-zero, this again looks like it's just negative mg dy integral from h to 0. And again, you get the same answer, mgh, which then equals delta t. And the fact you get the same answer in this case, you might be recalling, that's right, gravity is a conservative force, and there's something about how it doesn't matter how you get from point A to point B, which in that case, it doesn't matter which path. You could go straight down, you could take a ramp, you could take an arc, right? You could go up and then come back down. Gravity is a conservative force, which we will get to next time. But again, the mathematics here is that I parameterize my path, in this case in terms of the variable y, and then I turned into a 1D integral over y. Let me do one that's a little bit more interesting. Now, suppose I have a vector field here, where the vector field here is kind of the first quadrant of what would just be kind of vectors all moving in a circle. So it is negative y comma x is the vector field. It's a position-only vector field, right? It only depends on positions, not velocities. Or you might think this is a position-dependent force. That kind of looks like a churning circle. And I want to do a couple examples where I go from the origin, so 0, 0, out to the point 1, 1. So I want to start, start here, then end somewhere like here. But I want to do it in 3 different ways. I want to do it 2 ways that are exactly the same path, but I parameterize them different. So again, you can see that the parameterization doesn't matter. And then I want to do it with a different path compared to the first 2. So you can see how the answer can possibly change in this case, unlike it was for the gravity case, where both paths, even though straight down and at an angle, were quite different, though gave the same answer. That's because gravity is one of those funky gravitational or conservative forces. Let's do it for something more general. So let's do the first path, which I'll do in black. A path that just goes in a straight line. Just travels in a straight line from 0, 0 to 1, 1. Path 1. So again, first step is I need to come up with some sort of parameterization that will take me from 0, 0 to 1, 1. And so I'm going to parameterize the path by, and I'm going to have the path, I'm going to use s instead of t. I'm just going to do s, s with s ranging between 0 and 1. When s is 0, you're at 0, 0. When you go all the way up to s equals 1, you're at 1, 1. I think we all agree this would draw, this parametric equation would draw out a straight line that goes from 0, 0 to 1, 1. And what I'm doing is I'm giving a function for x, and I'm giving a function for y. Because remember, this, the general position is x, y, z for 3D, x, y in this case. So I'm saying that wherever I see an x, I replace it with s. Wherever I see a y, I replace it with s. And so then I can evaluate that the force in this case, which was negative y, x, that then becomes negative s, s. I can also evaluate dr by taking the differential of that path, which then looks like it's just ds, ds in this case. So then I've turned everything when I ultimately want to evaluate the work, which is an integral of f dot dr. This ultimately then becomes, it looks like negative s ds plus s ds when I do the dot product, which those cancel out. So it looks like this integral actually is just pretty simple and it's just 0 at the end of the day. If I want to be complete, again, this is an integral, maybe I'll be exact. Right, these cancel out, so really it's an integral of 0 over ds when s goes from 0 to 1, which of course is just 0. So in that case, no work was done as I moved across that diagonal line. And physically, you could think, why is that the case? Well, that's actually not too surprising, because for something that's where all the arrows are moving in a perfect circle, this 45-degree diagonal is always going to be the case that the force vector is perpendicular to the steps you're taking as you kind of march along. So the dot product, unsurprisingly, should be 0. Even though you're walking within a force field, you're walking perpendicular to the direction the force is being applied to you. As a result, you do not gain or lose any kinetic energy as a result. So there would be no change, no delta t overall. If you started that path with some non-zero velocity, you would have the same exact velocity once you got to the top. And again, what might be confusing is, again, you're parameterizing a path, which means you are constrained to be moving along that path. You might imagine that, well, why isn't the force kind of pushing you to the up and to the left? Well, again, if your path was free based on just the forces that are acting on you, right, that would be the case, right? Your velocity vector might kind of veer up and to the left. But on the case where you are constraining yourself to move along a particular path, this is how the forces acting on you ultimately change your kinetic energy. Let me now do the same path, but with a different parameterization. Let me now instead, let's see. Actually, let me do a different path, and then because it'd be nice to do one that gives me a non-zero answer. So let me do the path that kind of is more a parabola. It kind of does something like this. So this is my new path, something that kind of is a parabola that goes up. So in this case, the path I might use might be something like x, y, again, with s kind of going between 0 and 1. If you plot that parametric path, that would start you at 0, 0. You would end up at 1, 1. That would take you from the start to the end point. dr in this case looks like it's then just ds, 2s ds. The force vector, which is negative y, x, well, y in this case looks like it's s squared, and x looks like it's just s in this case. Because again, this is telling you x and y. Your parameterization tells you what x is as a function of this parameter s. Which again, you could also use t, but since it's up to you to make this whatever you want, I like using s instead of t. So then this dot product looks like it's the integral of negative s squared times ds plus s times 2s ds. So that looks like it's 2s squared. So then this looks like the integral of s squared ds, and s goes from 0 to 1 in this case with our particular parameterization, which then is just a third. Now let me do the same path. So yeah, this was not the same path. So this was a parabolic path. Now let me do the same path, but let me have it go, let's say, s squared comma s to the fourth, as s goes from 0 to 1. It's not that hard to imagine that this would trace out the exact same path at the end of the day. It would be the same exact curve once you drew out the entire curve. If you were looking at animation as s went from 0 to 1, the dot might be at different places compared to the previous path at different times, but it would still trace out the exact same shape at the end of the day, and that's all that matters. It does not matter what the parameterization is as long as it traces out the exact same path, ultimately, from start to finish. So then dr in this case looks like it's 2s ds comma 4s cubed ds. The force, which is negative y, so negative s to the fourth comma x, so s squared. Then it looks like the integral of f dot dr is then going to be, negative s to the fourth dotted with 2s ds plus s squared times 4s cubed ds. Once I do the dot product, both of those look like it becomes s to the fifth power. There's a negative 2 and then a plus 4, so this looks like it's 2s to the fifth ds, again, as s goes from 0 to 1. And how does this simplify? 2s to the sixth over 6 from 1 to 0. And indeed, this gives you back 1/3. Again, it does not matter the parameterization you use as long as it draws out the exact same curve. All right. And last, let me do a path that goes in chunks. So let's do the path that starts here and goes out horizontally to 1, 0, and then goes up to 1, 1. Now, parameterizing this in terms of a single curve is going to be challenging, so just do it in pieces. I'm out of room. So we'll just do it in steps. The first step will go completely horizontal. So again, the path to take this first step might be, well, I might just go s from 0 to 1, and then y is always equal to 0. Again, because this is x, this is y. Y is always equal to 0 in this case. So state that y is equal to 0. Then f, not f sub g, then f in this case looks like it's negative y, so negative 0, comma x. dr looks like it's ds, comma 0. The line integral looks like, well, in this case, it looks like I just get 0 plus 0 over ds. Because the dot product matches those two, and then the dot product matches those two. All right, so first leg of my journey, no contribution in that case. Again, unsurprising. If you go back to the image, your path is always perpendicular to the direction that the arrows are moving. So I would expect that as I take little steps perpendicular to the force, it is not going to change my kinetic energy. Then I start stepping my way upward. Well, in this case, the path I might take might be, well, x now is always equal to 1, and y now ranges from 0 to 1. That would take me from the corner, 1, 0, and take me all the way up to 1, 1. See, negative y, x. It looks like when I do this dot product, I get just the integral of 1 times ds from 0 to 1. This looks like it's just then 1 at the end of the day. Let's see, did I make a mistake? I did make a mistake. The dot product. Maybe I didn't. Did I make a mistake? Let's see, so this is x, this is y, so this is negative y. Oh, nope. That's just the derivative of that, so 0, ds. This is negative y, and this is x. And so then I get 0 dotted with minus y, and then ds. Yeah, okay. So, mistake in my notes, but this is correct. So in this case, then, the total work that's being done then is just 1, right? The sum of the two components. So in this case, notice that different paths resulted in different values of the overall work being done. It seems like the red gave a work of 1. Blue, what did we say blue was? A third. Blue gave a third. And black in this case gave 0. Now you can imagine what are some properties of these integrals, that follow from the usual integrals we know. If I did the path in reverse, what might you imagine if I started at 1, 1 and went to 0, 0 through these exact paths? You bet that it would just be a negative sign. That's a nice property of position-dependent forces. That might not be the case if you had a more complicated force that depend on your velocity, right? Think friction. If I go one way, it slows me down, but if I go the other way, it's not going to speed me up suddenly. I'm going to slow down in both cases. So in that case, I would say that I get negative work for friction in both cases. The work will always be negative because it will slow me down. In this case, when it's position-dependent forces, you can take the path backwards and you'll get the same answer with a negative sign. And we'll need that in the next lecture when we start talking about what it means to be a conservative force, which means that I can take any possible path in getting from point A to point B, and the work it does will be exactly the same. This force I've drawn here is an example of a non-conservative force. Different paths resulted in different amounts of work being done, unlike the case above with gravity, where the two examples we gave you the same answer. How can we more generally prove when the path doesn't matter? Well, we'll have to wait and do that next time.